Good morning and welcome to our webinar, Automotive Security Overview. My colleagues Borislav Nikolov and Bernhard Schrammel will give you a short introduction. Bernhard, please.
Thank you. Good morning.
Good morning.
Let us start with automotive cybersecurity from a European perspective. Let me explain the legend. CS is the abbreviation for cybersecurity. CSMS is the abbreviation for Cybersecurity Management Systems, and SUMS is the abbreviation for Software Update Management System. Standards are highlighted in this slide in gray, and regulations are highlighted in this slide in wine red. Let us take a look at the timeline. We are starting with this year and we are going until 2024. This year, the ISO 21434 should have been released. This is the related standard for cybersecurity. There's a slight delay in releasing this standard. We expect that it will be released during next year. When shall cybersecurity be considered in an automotive development project? The Annex D of the corresponding standard gives a hint. There are listed 10 questions. If any of these 10 questions can be answered with an yes, then your project is cybersecurity relevant. I give you two examples. Has your item a bus system? If the answer is yes, then you have to consider your project as cybersecurity relevant. The second question is, does your item have a software? If yes, then it is cybersecurity relevant. The UNECE Working Party 29 released two regulations for cybersecurity and for software updates. The R155 is for cybersecurity and the corresponding management system, and the R156 is for software and firmware update and the corresponding management system.
Hi, Boris is here. After the regulation becomes effective, the mandatory first step for the OEMs is to implement a cybersecurity management system. What is this system? What is cybersecurity management system? What could you imagine about it? You need, in summary, a set of processes forming a management system. Every management system consists of following 5 common steps. First step, appoint a person with overall cybersecurity responsibility. Second one, identify the cybersecurity risks in your organization. The third one, mitigate those risks with cybersecurity solutions. The fourth, issue cybersecurity policies based on your risks. And the fifth one, but not least one, train your staff on your risks and policies, and then test the awareness. From July 2022 on, the CSMS certification shall be considered for the type approval. In other words, it is mandatory for new models. The definite timeline will be communicated from the regulation body. From July 2024, the CSMS and the electronics known as EE certification shall be considered for the type approval of all models. The ISO 5112 planned for mid of 2021 gives guidance on organizational audits with respect to cybersecurity engineering. It is based on the ISO 21434 and is intended to be used to audit a CSMS as defined by the UN regulation. The ISO 24089 is expected in Q1 2022 and will handle software update engineering for road vehicles. Here the scope is software update over wire or over the air. Bernhard?
Also for automated driving, cybersecurity shall be considered. There's a generic guideline available for automated vehicles for level 3 and 4 according SAE 3016. And this says cybersecurity is a topic of the certification. The first available specific regulation is for the automated lane keeping system, the ALKS. This is brought by the Working Party 29 with the regulation 157. For the type approval of the ALKS system, the following certifications shall be available: for software and firmware updates and the corresponding software update management system, and cybersecurity and the corresponding cybersecurity management system. You see a typical product lifecycle with a focus on cybersecurity and updates. Almost on the right, you see the transition from production to operation. And the basis is two management systems, the cybersecurity management system and the software update management system. Typically, a project starts with a proof of concept. Security and updates shall be an integral part of the product lifecycle. This is required for the development and the verification and validation phase. During this phase, also process requirements, for example, like from ASPICE or CMMI, shall be taken into account. For the type approval, Working Party 29 delivered already these two regulations. The R155 for cybersecurity and the corresponding updates, the corresponding management system, and the R156 for software and firmware updates and the corresponding management systems. CSMS and SUMS shall also consider the production phase. When vehicles are in the field, we are talking about an operational life cycle. Requirements for the OEMs and the Tier 1s are to consider cybersecurity events from the field. That means security events shall be analyzed and the useful steps shall be triggered. For example, security measures shall be developed, tested, and the updates, SOTA or FOTA, shall be pushed to the vehicles in the field. From the IT domain, it is known as SIEM, which means Security Information and Event Management.
Now let us zoom into the development life cycle. Therefore, we take a simplified V-model view to explain some details. The OEM is developing on vehicle level on the left side. Therefore, the regulation of UNACE VP29 is in charge. On supplier level, in other words, the item level shall be considered. On the left side of the V-model, the development activities are displayed. On the right side, the validation and verification are shown. With the vehicle threat analysis and risk assessment, in short, TARA, the security relevant assets of the vehicle are outlined. That means all threats and risks are analyzed and rated. If the supplier sees more assets on its level as the OEM, then we recommend performing a separate TARA on item level. Let's look on verification and validation side. We zoom into the hardware and software level. For verification, reviews shall be done from security perspective. Experienced experts are required here. And tool support helps to improve the quality and reduce the effort. Another method for verification is vulnerability scanning. The next two examples are for validation, for example, fuzzing and penetration testing. Bernhard?
Heavens is a method of several methods for a threat analysis and risk assessment, in short TARA. Heavens is the abbreviation for healing vulnerabilities to enhance software security and safety. The definition of risk in general is a function of severity and frequency. This is also the same for hazard analysis and risk assessment for functional safety. The orange axis represents a frequency. The frequency axis shows the likelihood of an exploit of a threat. This corresponds with the threat level of the TARA. The red axis, the severity, presents a potential damage of one related system axis. This corresponds with the impact level of the TARA. The two colors are always the same for the next slides. This TARA allows you to analyze risky systems from a cybersecurity perspective. This is the risk graph according to the Heavens method. The goal is to determine a level of risk resulting from cybersecurity perspective. This level represents the level of risk without any implementation of countermeasures. With the implementation of countermeasures, an acceptable residual risk can be reached. Let me explain the two axes. With red, the impact level, it can have values from no impact to critical level, and orange again, the threat level, which can have values from none to critical. With the impact level and the threat level, a cybersecurity assurance level can be determined. The abbreviation is CAIL.
So the ISO standard 21434 gives no rules which methods shall be used. Your experts have the option to pick the best suitable method for your product. Some of the popular methods are Heavens, Evita, Octave, Sahara, Mora, OWASP, and so on. Now let's start with an example of evaluating the threat level. We need to estimate 4 parameters for each threat. Each parameter has values from 0 to 3. Let us look at the first one, expertise. 0 means layman. In other words, no expertise is needed. And the highest, the third, 3 means multiple experts. In other words, more than one expert, for example, hardware, software, or system experts are needed to execute the threat, to exploit the threat. The next parameter, knowledge of TOE. What is TOE? TOE is a target of evaluation. Zero for this parameter means that no information about TOE is publicly available. 1 stands for restricted. That means access to this information is shared within one organization and with other organizations under a non-disclosure agreement, shortly NDAs. A good example for this are requirements and specifications. 2 stands for sensitive information. In other words, the information or the knowledge is shared only within the specified developer team within a development organization. A good example for this is the software source code. Now the third 3 stands for critical. That means that this confidential information is needed and shared between a limited number of experts within a development organization. A good example is the secret root signing key. Now the threat level is summation of all 4 input parameters, each from 0 to 3, and the output are 5 threat levels from known to critical. The threat level is calculated without countermeasures, as already Bernhard said. But why? Like functional safety, we evaluate informed worst-case scenarios. And from there on, we take countermeasures to reduce the risk. The challenge here is to find an accepted residual risk for each threat. Okay. On the last slide, we showed you a calculation of the threat level. It has 4 parameters with Heaven's method. Let us look a comparison to another method, for example, Open Web Application Security Project, OWASP. For the threat level, this method has only 3 parameters. They are almost the same with the Heaven's method. That's why we will concentrate on the 4th one, the equipment. Here is not relevant. But why? Because, for example, every personal computer or computer has nearly the same capabilities. That is the reason why it is missing here. Without considering the equipment in the context of automotive domain, the results of the analysis are shifted. Out of this, keep in mind that picking the suitable method is very important for your product cybersecurity. In summary, we explained some parts of the calculation of the threat level. On the other side, the impact level categorizes the impact. Each attack path has impact on safety, financial, operational, and privacy aspects of the product. Both results give us a cybersecurity assurance level, shortly called CAL. The CAL indicates the item risk from a cybersecurity point of view. Depending on this risk, a certain level of assurance action is required. Let's look on the table, left top. It is categorized with quality management, low, medium, high, and critical. We know them from safety. The QM means no assurance level or action is attached. And let's look at the medium. You should take some actions here. For high and critical rating, it is required to take actions. Please take care to see the difference. Medium should take and high and critical required to take. The standard do not predefine the measures for each CAL level. Here each company should define such themselves. Of course, with the according argumentation. Our presented risk profile is an example. The standard 21434 offers also other risk profiles. Your experts may choose the appropriate one. What means countermeasures? This means that there should be enough resistance against penetration attackers. What means also resistance? In other words, implement countermeasures like against buffer overflows we used for elevation of privilege, input checks, output parameter checks, boundary checks, and test them on source code level. Let's go further and see how you would be able to categorize the attacks. We use the so-called onion layer model. It is a categorization based on the location of the attack. In other words, from which place has the attacker an attack path to the vehicle? Layer 1, a remote access to the relevant systems over the internet is possible. The attacker can be anywhere in the world where internet access is available. Layer 2, short distance, near field communication, for example, Care2X, Bluetooth, TPMS, and so on. In this case, the attacker must be near the vehicle, but it is outside of it. Layer 3, there are existing and unrestrictedly accessible interfaces in the vehicle. That means the attacker is in the car when he starts an attack on this layer. Or the other possibility of a successful attack is via layer 1 and layer 2. That in this case, that means that the attacker has successfully executed a longer attack path. For layer 4, without any disassembly work, there is typically no direct access to bus systems in the vehicle. As explained for layer 3, the attacker must take longer attack path in order to get here. The smallest impact on this level is to disturb the communication on the buses, for example, denial of service. And the last layer, layer 5, when the attacker gets access to the ECU or the electronic control unit, then he might be able to have an impact on the expected functionality of the vehicle. So you see that our model has the form of onion. Now let's finalize our presentation and summarize it. We show you an example of cybersecurity assurance level determination on layer 4. And that means For this example, we analyzed a target of evaluation on system level with interfaces for layer 4. The starting point for the analysis is to define the cybersecurity relevant assets. The next step is to analyze the possible damage scenarios for each asset. In this example, several assets have the same damage scenarios. You see the 6 connections from assets to one damage scenario. With damage scenarios, we evaluate the impact level using the 4 parameters: safety, financial, operational, and privacy. Now let us look at the interfaces. Each asset has one or more relationships to the interfaces. For example, can signal is an interface. Every interface has one or more possible threads at the bottom. To determine the possible threads, the Microsoft thread method can be used. Also can be done. And in our example, we used a tool from Austrian Institute of Technology, shortly AIT, named thread-get. As we already mentioned, when all possible threads are defined, the threat level can be determined. Every damage scenario can have one or more attack paths. One dashed and one dashed dot line shows the relations. Each line shows an attack path. For every attack path, the impact level and the threat level shall be evaluated. So we come to the CAL, cybersecurity assurance level, for each attack path. Bernhard?
So thank you, Boris. And now the next steps are you should continue with series development and with the verification and validation phase. So thank you for listening to our webinar. We are happy that we could give you some information, and if you need also support from us, we are able to do it.
So thank you for your attention, and if you have any questions, the next slide will show you the contact details from our colleagues. Okay, thank you.
Thank you.